Hi! In this tutorial we will have a look at the multiple linear regression. As you already know from the previous tutorial, we use multiple linear regression when we want to predict an outcome variable from several predictor variables. Multiple regression tests the relationships between these predictors or independent variables and an interval scale dependent variable. The interpretation of the partial regression coefficients will be the expected change in the outcome variable when one predictor is changed by 1 unit and all other predictors are held constant. Don't worry about this too much at the moment. I will explain it once we will have the outcomes, the results. The equation will have a bit longer format now, and their general form looks like this. Also, we will come back to this in 1 second. We will use the same example as for the simple regression. You want to suggest a marketing plan for the next year that will result in high product sales. Now we have more variables to work with. We have the sales of music downloads in thousands of units, the advertising expenditures in thousands of euros again, the number of radio plays an artist received per week, so the airplay, and then we have the start power, which is the popularity rating of an artist based on the release history. We will also extend our question. So in addition to the influence of advertising, we are now interested in estimating the influence of airplay and star power on the number of album downloads. The equation will now look like this. Advertising, airplay and star power will represent the observed data, and beta 1, beta 2 and beta 3 represent the relationship between sales and advertising expenditures, radio airplay and star power. It tells you by how much sales will increase for an additional euro spent on advertising when radio airplay and star power are held constant, also by how much sales will increase for an additional radio play when the rest is held constant, or by how much sales will increase for an additional star power when the rest is held constant. Like in the simple regression, the plane is fitted to the data with the aim to predict the observed data as good as possible. Let's run the multiple regression in RStudio now. We will first load our data set, and then we can use the lm function to run the analysis. So let's load the data. We have the lm function here. We just need to separate the individual predictors using the plus symbol. Our results will be assigned to the object called multiple regression that we have here. And in the arguments we will first specify our outcome variable, which is sales, and then we will use again the tilde sign, and then we specify all independent variables, so advertising expenditures, airplay and star power. Then we add the argument data to specify the data frame we are working with, in our case regression. Let's run it. Perfect. And then we will use the summary command to display the output. In the output we can see the estimated coefficients beta 1, beta 2 and beta 3. It's this estimate column, the first one. I'm not able to highlight only that one. For advertising expenditures, we can say that when advertising expenditures increase by 1 euro, sales will increase by 0.08 units. For airplay, we can say that when radio airplay increases by 1 play per week, sales will increase by 3.37 units. And for star power, we can say that when the star power rating increases by 1 scale point, sales will increase by 11.09 units. Then we also have the t-values and p-values in the output. It's these last two columns. And we can see that the p-values are smaller than 0.05 for all three coefficients, so we can say that all effects are significant. And again, To get a better feeling for the range of values that the coefficients could take, we can compute confidence intervals by using function confint, which is up here. So let's run this command. And in the output we can see the table. Well, for example, let's take star power as an example. The confidence interval for star power is 6.28 and 15.89. So although we have computed a point estimate of 11.09 here, the effect might actually just as well take any other value within this range from 6.28 to 15.89. The output also displays the multiple r squared and adjusted r squared, and it tells us, the multiple r squared tells us that 66.47% of the variation can be explained by our model. Now we can use the estimated coefficients to predict sales for different values of advertising, airplay and star power. Let's suppose we would like to predict sales for a new music album with advertising expenditures of 800 euros, airplay of 30 and star power of 5, and we want to find out how much the album will sell. We will use the estimated values and the corresponding advertising, airplay and star power values in the formula and calculate that the predicted value is 198 units, and that means that our product will sell 198 units. You can also calculate this in RStudio easily. We will use the same equation where the coefficient 1,1 is the intercept, coefficient 2,1 is the advertising expenses, and times 800 euros spent on advertising. Then we have coefficient 3,1, which refers to airplay, and 30 airplays per week. And last but not least, we have the coefficient star power and the number of 5. Okay, let's run the command, and now we can see the result of 198, which is exactly the same what we got by calculating it with the equation. Okay, there is one more thing I would like to mention regarding interpretation of coefficients from linear regression. The output from the model helped us to formulate and predict outcome variable, but it is difficult to compare the effects of the independent variables because they are all measured on different scale. For example, in our case, euros, radio plays, and so on. So in order to be able to judge the relative importance of the predictor variables, we have to use standardized coefficients. We can get the standardized regression coefficients by multiplying the unstandardized coefficients by the ratio of standard deviations of the independent and dependent variables. So the standardized coefficient will tell us by how many standard deviations the outcome will change when the predictor variable is changed by one standard deviation. And we can easily compute the standardized coefficients using this lm beta function, but we need lm.beta package for this. So first of all I will load the package, and now we can use the function lm.beta. Perfect. Let's have a look at the output. The results show that for advertising spendings and for airplay, a change by one standard deviation will result in a 0.51 standard deviation change in sales, whereas for star power, a one standard deviation change will only lead to a 0.19 standard deviation change in sales. So, while the effects of ad spend and airplay are comparable in magnitude, the effect of star power is not so strong. So by using standardized coefficients, you can even compare the effects. That's all from my side for the multiple regression. Thank you for watching the tutorial.